In this video, I will be discussing about the area of a surface of revolution. The surface area we know is the total area of the outer layer of an object. Now, while objects such as cubes or bricks, the surface area of the object is the sum of the areas of all its faces. Then, for curved surfaces, the situation is a little bit more complex. So here, before I will discuss the procedure of how to find the surface area of a surface of revolution, allow me to derive first the formula of finding the area of that surface of revolution. Now, suppose we want to find the surface area of a frostum of a cone. So, suppose this is the cone. So I will be drawing here cone, and suppose this is the radius of the cone, say r sub 1, and it has a slant height of say s, but because a frostum is just a part of a cone, that we take out the upper portion of the cone, so this one here. So this solid line is just illustrating the frostum of a cone, this one here. And suppose this length, which is the slant height of the frostum of a cone, say this is represented by L, and the radius of the upper base, suppose this is r sub 2 here, and the axis of the cone is this one here. And we know that the lateral surface area of a cone is equal to pi r sub 1 s. So this is the formula of finding the surface area of this whole cone. And since the cross sections of the small cone and the large cone are similar triangles, and so to have a better picture, we can draw this cross section of the bigger cone, the whole cone, whose radius is r sub 1 and whose length of the slant height is s, this one. But for the smaller triangle, this one here, it has a side of r sub 2 because this is the upper base of the frostum, and the slant height is L, this one. Then therefore, the length of this side, the length of this hypotenuse of this smaller triangle, which is the cross section of the smaller upper cone, is the whole s minus L, because the whole side, this side, the hypotenuse of the cross section of the whole cone is s, and since this side from this point up to this point, the length is L, then therefore if you subtract s by L, the remaining side is s minus L. So we can make a proportion here that the ratio of the smaller side to the larger side, r sub 1, this one here, this r sub 2, when divided by r sub 1, is equal to the quotient of this smaller hypotenuse, which is s minus L, divided by the whole hypotenuse, which is s. And if you multiply both sides of the equation by s, we have r sub 2s, and also multiply both sides of the equation by r sub 1, we have s minus L times r sub 1. And distributing this r sub 1 to this binomial, we have r sub 2s is equal to r sub 1s minus r sub 1l. So moving this term to the left hand side of the equation makes this term a positive term, And also moving this term to the right hand side, this becomes a negative r sub 2s. And then we can factor out our common factor, which is s. So s times r sub 1 minus r sub 2 here. Then therefore, if we divide both sides of the equation by this term, r sub 1 minus r sub 2, we have r sub 1L divided by r sub 1 minus r sub 2, which is equal to s. Then with this, we can find the lateral surface area of the frostum. This one here, which is equal to the lateral surface area of the large cone, the whole cone, minus the surface area of the small cone. So common sense would tell you that to find the surface area of this frostum is the surface area of the whole cone minus the surface area of this smaller cone at the top. And we know that the formula for the whole surface area of the large cone is pi r sub 1s. So we will write here pi r sub 1s. And this will be subtracted by the surface area of the smaller cone. Okay? So this is pi r sub 2 times the length of the side, which is this one. So the length of this up to this one is s minus l here. So instead of writing our s, we will write the side s minus l, because this is the slant height of the smaller cone. And so that you will not be confused of this s from this s here, I will write ls here to mean that this is the lateral surface area of this frostum here. And then we can substitute the value of our s here, because we know the value of s is this one here. So instead of writing the s, I will write its equivalent expression, which is equal to r sub 1 L divided by r sub 1 minus r sub 2. And this will be subtracted by pi r sub 2 times our s again, which is r sub 1 L divided by r sub 1 minus r sub 2 minus L here. And then we can multiply this pi r sub 1 to this r sub 1 L, and the product is pi r sub 1 squared L. And this will be divided by r sub 1 minus r sub 2. And this will be subtracted by this pi r sub 2, and then we combine these two terms here with the common denominator of r sub 1 minus r sub 2. So this is r sub 1 L minus L times r sub 1 minus r sub 2 there. And then we can simplify this expression, the second term there, in our formula of the lateral surface area of the frostum by distributing this L to this binomial here. So this becomes r sub 1 L minus r sub 1 L plus r sub 2 L divided by r sub 1 minus r sub 2 there. And then we have our lateral surface area, which is equal to pi r sub 1 squared L divided by r sub 1 minus r sub 2 minus the pi of r sub 2 times the fraction. This one can be cancelled, so what remains is r sub 2L divided by r sub 1 minus r sub 2 here. So our lateral surface area of the frostum is pi r sub 1 squared L divided by r sub 1 minus r sub 2 minus pi r sub 2 squared L divided by r sub 1 minus r sub 2. And since the two fractions are having the same denominator, we can combine them as one and factor out the common factors, which are pi L. So this will be multiplied by r sub 1 squared minus r sub 2 squared divided by r sub 1 minus r sub 2. And since this is a difference of two squares, we can factor them as r sub 1 minus r sub 2 times the quantity of r sub 1 plus r sub 2. So that factor of r sub 1 minus r sub 2 can be cancelled with the denominator. So what remains is that the lateral surface area of the frustum is pi L times r sub 1 plus r sub 2. So this is now our formula in finding the surface area of this frustum here. Thus, we can use this formula of the surface area of the frustum of a cone to calculate the area of a surface of revolution. And since our goal here is to derive the formula in finding the area of a surface of revolution, so we need to consider a non-negative smooth function y equals f of x over a closed interval from a to b. And suppose this is the graph of the smooth function. So this has an equation of y equals f of x, and this is a continuous function over a closed interval from a to b. So with this, there is an area enclosed by this function over a given interval. And suppose we want to rotate this area about the x-axis, you form a solid here like this. So suppose this is our solid that is formed by rotating this area about the x-axis, this one. Our goal is to find this surface area and not the volume of the solid. So by intuition, we can slice the whole surface into smaller pieces. And suppose this is one of the smaller slice, this one here. So if we magnify this slice here, this is our slice, and at this point, suppose this is having a y of f of x sub I. This point here is having an x before x sub I. So this is f of x sub I minus 1 there. And we call this one as the incremental slice. If we slice the whole surface into infinitely many slices. So therefore, we can approximate the area of this incremental slice, because if you cut at the side, you will get a long rectangular piece whose area, so we represent this area as the delta surface as pi times r sub 2 plus r sub 1 L. Because this is the formula that we have derived, the formula of finding the surface area of a frustum of a cone. And this looks like a frustum of a cone here, because if you draw a dotted line, you form a cone. So I'm just using the formula that we have derived in finding the surface area of this frustum of a cone. And we know by substitution that this incremental surface area, when we slice the whole surface into many slices, we have pi times r sub 2, which is this one here, the smaller radius here, which is f of x sub I minus 1 plus f of x sub I, the radius of the bigger base. And this will be multiplied by our L, which is the slant height of this incremental Frostum. So this is our L. But we know already what is the value of this incremental slant height, that this is the one that we derived in the previous video, which is equal to the square root of delta x quantity squared plus delta y quantity squared here. Because if we do magnify this slant height, this is having a vertical increment of delta y and a horizontal increment of delta x. So to find this incremental length L is to use the Pythagorean theorem, which is this one. And then we can apply a little manipulation here, which is to multiply the radicand by something that makes the first term in the radicand equal to 1. So if we multiply the whole term by delta x quantity squared and divide also delta x quantity squared here, I was not able to alter the value of the radicand because delta x squared divided by delta x squared is just equal to 1. So we have our delta s, which is equal to pi times f of x sub I minus 1 plus f of x sub I is multiplied by this square root of 1 added to delta y over delta x quantity squared, but this delta x squared can be factored outside as delta x. So by the mean value theorem, there exists some value x, so we call it x sub I asterisk, which can be found in the closed interval of x sub I minus 1 to x sub I, such that the derivative of this function at x sub I asterisk is equal to delta y over delta x. So our formula, which is the delta s, can be written as pi times f of x sub I minus 1 plus f of x sub I, which will be multiplied by the square root of 1 plus this one. I can replace this delta y over delta x by this one. So we have f prime of x sub I asterisk quantity squared delta x. And since f of x is continuous by the intermediate value theorem, there exists, you can always find x sub I double asterisk that is found in the closed interval of x sub I minus 1 to x sub I, such that the f of x sub I double asterisk is equal to 1/2 of the function f of x sub I minus 1 plus f of x sub I. And we know this one, the intermediate value theorem, from our previous calculus 1. And then multiplying both sides of the equation by 2, we have 2 times f of x sub I double asterisk is equal to the sum of f of x sub I minus 1 plus f of x sub I here. So therefore, our incremental surface area is equal to pi, this one, times this one. But this one is equal to this. So instead of writing that one, I will write times 2 times f of x sub I double asterisk here. And this will be multiplied by the square root of 1 plus the square of the derivative of the function at x sub I single asterisk here. So therefore, to find the surface area of this whole surface of revolution, we can add all the surface area of all the slices. So we say that the whole surface area is the sum of all incremental surface areas there, which is 2 pi, if you multiply this one and this one, 2 pi times f of x sub I double asterisk times the square root of 1 plus the square of the derivative of the function at x sub I single asterisk here. However, if you slice the whole surface area of revolution into infinitely many slices, this one from A to B, then both x sub I single asterisk and x sub I double asterisk approaches to x. So we write here the whole surface area is equal to the sum of all surface area of all incremental slices, which is given by 2 pi times f of x times the square root of 1 plus f prime of x quantity squared delta x. And there are how many slices? There are actually infinitely many slices here. So I just replace x for this one and this one, because these values will approach x when you slice the surface into infinitely many slices. And then we realize that this is a limit of a Riemann sum. Then therefore, we write that this is the integration of all surface areas from incremental surfaces, which is given by this 2 pi times f of x times the square root of 1 plus the square of the derivative of f dx from A to B, because we will be slicing the whole surface from A to B. So from here up to here. And if you're going to analyze this area, this is just the circumference of the incremental slice. And then this one is our slant height, incremental height L here, which is the formula of finding the arc length. So this is the ith arc of the incremental slice times the circumference of the incremental slice. So we can generalize here that the formula of the surface area of revolution can be obtained by integrating 2 pi times the radius of the incremental slice times the ith arc in the incremental slice. And this one is having this expression, and this incremental arc is this expression in the formula here. So now let's apply the formula that we have derived in example number 1 here. Find the surface area of the surface generated by revolving the graph of the curve y equals the square root of x around the x-axis over the closed interval from 1 to 4. And we know that the graph of that equation is a parabola opening to the right. And considering this one, in the interval from 1 to 4, we rotate the graph around the x-axis. So the solid of revolution that we can form here is this one. So this is the solid of revolution. But our goal is to find the surface area of this solid of revolution. So by intuition, let us slice the whole surface. And suppose this is one of the slices that we can take from this surface of revolution. So if we take this out here so that you can have a good picture, you can have this incremental slice in this drawing and determine the radius of this ring. And the radius of this ring is the y of the equation. So y is the function of x. And we know that this is our ith arc. So this is our ds here. And since the equation of the curve is y equals the square root of x, which can be written in the exponential form x to the power of 1/2, we can find its derivative. And its derivative is 1/2 x to the power negative 1/2. Or you can write this derivative as f prime of x, which is equal to 1 over 2 square root of x if you write this one in radical form. Then with that, we can formulate our equation in finding the surface area of surface of revolution as the integral from 1 to 4, because you will be slicing from 1 to 4 here of the circumference of the incremental slice here. So we have 2 pi times the radius of f of x times its thickness, which is our ith arc, our ds, and we know that the ith arc is having a formula of 1 plus the square of the derivative of our radius. And substituting this derivative and this function here, we have the total surface area is obtained when we integrate 2 pi times our f of x, which is square root of x, this one. And then this will be multiplied by 1 plus the square of its derivative. So when we square 1/2 over square root of x, this is 1 over 4x dx here. Because when we square this derivative, the square of 1 over 2 square root of x, this one, is equal to 1 over 4x. And factoring this constant of 2 pi as well as combining these two terms, we have the whole surface area is equal to 2 pi times the integral from 1 to 4 of the square root of x times the square root of a single fraction having a common denominator of 4x. So this is 4x plus 1 here. And then applying the properties of radicals, we have 2 pi times the integral from 1 to 4 of the square root of x times the square root of 4x plus 1 over the square root of 4 times the square root of x dx. So therefore, we can cancel the square root of x with this one here. And we know that the square root of 4 is 2. So we can factor it outside. So 1/2 here times the integral from 1 to 4 of this 4x plus 1 to the power of 1/2. Because if you write the square root of 4x plus 1 in exponential form, this is the answer. And if we represent this 4x plus 1 as our u, we realize that the differential of u is 4 dx. And dividing both sides of the equation by 4, the result is dx. There. So substituting these representations to this expression here, we can write our whole surface area as pi, because this 2 in the denominator and this 2 cancels each other. So pi times the integral of u to the power 1/2, because instead of writing 4x plus 1, I will write its equivalent expression, which is u. And this is multiplied by du over 4, because instead of writing dx here, I will write its representation du over 4. And now we can factor our 4 outside the integral. So this becomes pi over 4 times the integral of u to the power 1/2 du. But since our variable is changed from x to u, then our limits will be changed from 1 here to 5 here, because if you substitute 1 in this representation, 4 times 1 is 4 plus 1 is 5. So when x is 1, the u is 5. And when your x is 4, so substituting 4 here, 4 times 4 plus 1, that is 17. So our limits of integration will be changed at this time. So the whole surface area, which is equal to pi over 4 times the integral of u to the power 3/2 over 3/2, because this is the integral of u to the power 1/2 evaluated from 5 to 17. So therefore, our surface area is equal to pi over 4 times 2 over 3. And this will be multiplied by this u to the power 3/2 and substituting the upper limit here. So this is 17 raised to the power 3/2 minus 5 raised to the power 3/2 also here. So therefore, our surface area is equal to pi over 6, because this 2 and this 2 here cancels each other. So what remains is a factor of 2. So 2 times 3 is 6. And this will be multiplied by 17 times the square root of 17, because 3/2 is 1 and 1/2. So 1/17 times the square root of 17 minus 5 times the square root of 5, because again the exponent is 3/2 there. And if you're going to use your calculator, this is approximately equal to 30.85. And this is the surface area of the solid of revolution. Now let's proceed to our example number 2. Determine the surface area of the surface generated by revolving the graph of this function cube root of 3x around the y-axis over the interval from 0 to 2. And since we are revolving the curve around the y-axis here, and the interval which is in terms of y, so from 0 to 2 here, so this is 2. So we need to rewrite the function in terms of y, because we are revolving around the y. So this one, which is equal to the cube root of 3x, our y, we can solve for x by cubing both sides of the equation. So this is y cubed, which is equal to 3x. And then dividing both sides of the equation by 3, we have y cubed over 3. So this is our function in terms of y. So say we name it as g of y, and this is 1/3 of y cubed. Then therefore, we can solve for the derivative of this g of y. And the derivative of this is 1/3 times 3, which is 3 over 3 y squared. So therefore, our derivative of g is equal to y squared here. And sketching the graph of this cube function, the graph is this one here. And you can check this graph using a graphing calculator. So revolving this graph about the y-axis, you form a solid of revolution, which looks like this one here. So this is now our solid of revolution, this one. And if we're going to slice the whole surface from 0 to 2, so from here up to here, and get one slice, this one here. So suppose this is our one slice in this drawing, and magnify this slice here. So this is our slice. We know that this is our ith arc. So this is our ds here. And then for the radius of this incremental slice, it's actually the x of our curve. So this is our g of y. X function in terms of y. Thus, our whole surface area, which has a formula of the integral from 0 to 2 of the circumference of the slice 2 pi r times the ith arc length of ds. So this ds is this one, the thickness of the slice, and this 2 pi r is the circumference of every slice. So we have the whole surface area is the integral from 0 to 2 of 2 pi x, but our x is the g function. So this is in terms of y. So this is 1/3 of y cubed. And why do we need to change it to y? Because we are rotating, revolving about the y here. And this will be multiplied by the ith arc. And we know that the arc length is represented by the square root of 1 plus the derivative of our g function, which is in terms of y here. So we square this one times dy. So the whole surface area is equal to 2 pi over 3 if you factor out this constant outside the integral. So 2 pi over 3 times the integral from 0 to 2 of y cubed times the square root of 1 plus the square of this derivative. So this is y squared raised to the second exponent here. And rewriting this expression, we have 2 pi over 3 times the integral from 0 to 2 of the square root of 1 plus y to the 4th times y cubed dy. And using integration by substitution, we can use this radicand as our u. So u is equal to 1 plus y to the 4th. And solving for the differential of u, we have 4y cubed dy. But we don't have the 4 here, only y cubed dy here. So we need to remove the 4 by dividing both sides of the equation by 4. So this is y cubed dy, the expression equal to du over 4. So by substitution, we have the whole surface area, which is equal to 2 pi over 3 times the integral of this one, 1 plus y to the 4th. So instead of writing that 1, I will write u, but this will be raised to the exponent of 1/2. And instead of writing this one, I will write its equivalent expression, which is du over 4. So this is du over 4. So instead of writing 1 plus y to the 4th, I will write u, because that is the representation of that. And instead of writing y cubed dy, I will write its representation du over 4. And we can factor out this constant of 4 here outside the integral. So we have 2 pi over 12 here times the integral of u to the power 1/2, which is u to the power 3/2 over 3/2. And since we are changing the variables from y to u, we will change the limits of integration from 0 to u. So when y is 0, our u is 1. So this is 1. But when your y is 2, so 2 to the power of 4 is 16 plus 1, it's 17 here. So this is from 1 to 17. So this is evaluated from 1 to 17. So our whole surface area is equal to pi over 6, because if you reduce this 2 over 12, we've got 1/6 here. And then this will be multiplied by 2 over 3, which is the reciprocal of 3/2 here. And this is multiplied by u to the power 3/2, which will be evaluated from 1 to 17. So our surface area is equal to pi over 9, because this 2 here and this factor of 2 from 6 cancels each other. So what remains is 3. So 3 times 3, the product is 9. And this will be multiplied by this expression. So when you substitute 17 to the power 3/2 minus 1 to the power 3/2, here we've got our surface area, which is equal to pi over 9 times 17 times the square root of 17 minus 1 here, because 3/2 is 1 and 1/2. So we have one factor of 17 and the other factor is 17 to the power of 1/2. And you can use your calculator that this surface area is approximately equal to 24.12. And this is our surface area of the surface of revolution when we revolve this cube root of 3x about the y-axis over the interval from 0 to 2 in the y. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to map your way up. Thank you.